We are at the Institute of Electronics, Microelectronics and Nanotechnology in France, a research center with large-scale facilities which are dedicated to micro and nano fabrication processes. You have like 1,600 square meters of clean rooms where we can build electronic, optical, magnetic devices as well as microsystems for a wide range of applications. You might have experienced anechoic chambers, which are rooms designed to completely absorb the sun reflection. The room's side walls consist of periodic wedges made up of acoustic foam like the one you have here. It's the periodicity of the wedge, the pattern you have here, that restricts the sound propagation. And it's a universal concept. It applies to sound, but also to seismic waves, electromagnetic waves, as well as electronic waves. How can we play with electron waves and manage to control the electron propagation in a periodic structures? So that was a challenge of the project called Dirac III-V, funded by the National Research Agency, to produce Dirac electrons, which are electrons without any mass. And so by combining the honeycomb lattice of graphene with semiconductor heterostructures, we wanted to design new electronic states in materials. So it was important to work at IEMN, where we have all the nanofabrication tools and also the characterization tools for micro and nano processes.
So the main challenges was related to get smooth and well-defined interfaces between substrate and very thin quantum well. And to do this, we use a special growth technique, which is called molecular beam epitaxy, and for which we use very pure materials in an ultra-high vacuum chamber. And so the main challenge is what to get very smooth surfaces and interfaces within this technique.
Dans cette étape-là, le but, c'est de déposer une couche de protection avec un épaisseur 50 nano.
So we have just spin coated the resist on the wafer, and now we will use this tool, which is an EBPG 5000 plus of rates, which is able to write some patterns down to 10 of nanometers. For this project, we use this machine to write some dots of around 15 nanometers separated by 40 nanometers. The last stage will be after the beam writing, we will do the development of the resist. We will open the resist where the electrons go into the resist.
Et par la suite, l'échantillon il était transféré dans une autre bâtie de gravure qui s'appelle ICP et Rio pour transférer les trous qu'on a créés dans le masque dans la couche de InGas. On a créé notre réseau de quantique.
For this project, we have designed some device with a pattern between holes of 40 nanometers, and so we use the SEM to measuring precisely the dimension and if we have a deformation of the network.
As you may know, in SEM, we usually get a 2D image of the surface. Then with AFM, we're able to extract the real topography. So first of all, when we import our image in the mountains, we have to perform some corrections, some basic corrections. These AFM images, they allowed us to get the morphology of our sample on a relatively large scale, which allowed us to select appropriate image for further in-depth analysis by scanning tunneling microscopy.
The nanoprobe is dedicated to the electrical transport measurements on surfaces, nanostructures or devices at the nanoscale. This instrument is a unique tool, gathering many instruments in one, scanning electron microscopy, scanning tunneling microscopy, electrical measurements, and as well as optical, ultra-fast optical spectroscopy. All these measurements can be analyzed together in one single software, that is mountain software, in order to be able to correlate the results. So on this sample, we wanted to probe the conductivity of a quantum well. This was done in order to make sure that, this sample can be compatible with lower temperature measurements.
So scanning tunneling microscope is an instrument which works on the principle of quantum tunneling, and it allows us to get very good information about the surface morphology. It's a surface-sensitive technique, as well as the electronic properties using the scanning tunneling spectroscopy. So once the measurements have been completed and the data acquired, the next step is actually to treat the data and extract some useful information from it. This is where actually Mountain's software comes in handy, because it allows us to treat both topography data from the STM measurements as well as the scanning tunneling spectroscopy data.
So many researchers, engineers and PhD students at IEMN work together to solve the issue of nanoperforating a quantum well with a very small lattice parameter around 20 nanometer. The project was very challenging but rewarding when we were able to show the existence of specific electron state and find finally the state we were looking for. Mountains was key to progress through the different nanofabrication steps involving multi-physical analysis, and finally to prove the existence of electrons with very light mass or heavy mass.